So this video is going to look at intermolecular forces. Let's just be clear from the start that when we talk about intermolecular forces between molecules, we are therefore only talking about covalent compounds. But it turns out that most of the bonding questions at A level are now going to be directed more to do with intermolecular forces and their relative strength than to comparing, say, an ionic versus a covalent compound. So let's have a look at the three different types, how they arise, how we can tell whether a molecule has one or the other, and then how we can answer questions about comparing different molecules and the strength of their intermolecular forces. Okay, so the first thing to get into our head is that intermolecular forces, although they are weaker than the traditional types of bonding, like ionic and covalent and metallic, they are still essentially electrostatic attractions. So they always arise through attractions between dipoles across a molecule. So where the charge across a molecule is not evenly distributed and you have a slightly more negative charge on one side of the molecule than you do on the other. So the only difference between these three different types is how strong that dipole is, whether it's permanent or not. So we're going to look at instantaneous-induced dipoles, which you may also call London forces or van der Waals forces, permanent dipole interactions, and hydrogen bonding. And so at the moment they're in order of strength, but actually in terms of explanation it makes sense to start with the permanent dipole and then to look at hydrogen bonding and then look at instantaneous-induced dipoles last, just because it kind of flows a little bit better. Okay, so looking at permanent dipoles. Permanent dipoles arise from a difference in electronegativity. You need to know your trends in electronegativity and your definition. So further right and further up the periodic table makes more electronegative. So nitrogen is more electronegative than carbon, chlorine is more electronegative than hydrogen, and so on. We can label our bonds, and if you don't know how to do this, I suggest you just go back and have a little look at where these elements are on the periodic table. However, there is a little bit of a cheat. Most of the things that we're going to be looking at are organic molecules containing carbon and hydrogen. Just so happens that carbon and hydrogen are the least electronegative of the elements that form covalent bonds commonly. So if you look at my carbons, they are all delta positive, and if you look at the hydrogens, they are all delta positive. So any bond that contains carbon or hydrogen and another element, we can make a pretty safe assumption that carbon or hydrogen are going to be the ones that are the delta plus. They are the least electronegative elements. So actually it's pretty easy to work out whether something has a permanent dipole or not. So where do you find them? What sorts of compounds have permanent dipoles? It's actually easier to look at where you don't, because they're so common. So elements, of course you don't find them in elements because there's no difference in electronegativity if there's no difference in the atom. So molecular substances, molecular elements, Cl2, O2 and 2. The other thing to watch out for is a molecule that may contain polar bonds, where there is a difference in electronegativity, but the shape of the molecule means that there is symmetry and the overall dipole cancels, so there is no overall what we call dipole moment. Carbon dioxide is an example of this. It's linear. So even though those bonds are polar, carbon dioxide as a whole is not, because the two oxygens cancel out. The other place that you don't find permanent dipoles is in hydrocarbons. So alkanes, alkenes, and anything containing a benzene ring, assuming it has nothing else attached to it other than hydrogen and carbon. So hydrocarbons, we kind of assume that carbon and hydrogen with such close electronegativity values don't make permanent polar bonds. So actually, when it comes to deciding what does have permanent dipoles, it's basically any other compound. So if it contains a CO or a carbon halogen bond, if it contains nitrogen attached to a carbon, and of course if it contains any of those electronegative elements attached to hydrogen, then it contains permanent dipoles too. So it's easy to spot where the permanent dipoles are because there are not very many instances where there aren't any permanent dipoles. One thing that people do forget is they might look at that OH and think immediately of hydrogen bonding, which is true, but hydrogen bonding is a type of permanent dipole. So if it has hydrogen bonding, it will also have a permanent dipole. In fact, hydrogen bonding is what we're going to look at next. So hydrogen bonding is just a special type. It's like an extreme example of a permanent dipole attraction. So where you're going to find it? Well, if there is an F bonded to an H, which in fact is just HF, that's hydrogen fluoride, you can't have any other example. An O bonded to H, so alcohols and carboxylic acids. You'll do more about carboxylic acids next year. We haven't come across NH very much in the context of organic chemistry, but when you do amines and amides, you'll see it, and ammonia, which we should have seen before. So why is it a special type of dipole? Well, these three elements are in the top right-hand corner of the periodic table, which makes them the most electronegative elements on the whole periodic table. So they have the strongest ability to withdraw that pair of electrons that they're sharing with the hydrogen. So that delta negative is going to be extremely delta negative. And in fact, when you take away the electrons that the hydrogen is sharing, what you're leaving behind is basically just a proton. So you're leaving behind a really kind of unprotected positive charge with no shielding around it whatsoever. And so that hydrogen is really exposed to any other element which has a lone pair and a high electron density. So when it comes to drawing hydrogen bonds, there are three things we need to consider. The first thing is the dipole on the hydrogen that is attached to an oxygen, a nitrogen, or a fluorine. The second thing is the lone pair on the other oxygen, nitrogen, or fluorine, so the other element that's electronegative. And the third thing is that there should be a 180-degree bond angle around that hydrogen, because what's really being happening there is that the hydrogen is essentially being shared between those two oxygens. It's almost like the oxygen on the left is making a dative bond to that hydrogen because that hydrogen has had so much of its electron density pulled away from it that it's almost like a hydrogen ion. Now, it isn't a covalent bond, it's about 1/10. But the point is that hydrogen is kind of hovering in the middle and it needs to overlap the orbitals, the atomic orbitals of both of those atoms. The other bond angles, don't worry about them. They could look really messy if you want to. The main thing is to respect that bond angle there. So if I put my hydrogen in the middle and I make sure I draw that dipole, there might be other dipoles you draw, it's not as important. I draw that lone pair on the nitrogen, I draw the hydrogen bond in between, which is usually 3 little dashes, and then I just put in the rest of the molecule. So try to draw your hydrogen bond and then put the rest of the molecule in. That way you will keep the shape as it should be and the bond angles. What about hydrogen bonds between two different molecules? So let's have a look at something that we would not normally consider to form hydrogen bonds. So propanone does not have hydrogen bonding between its molecules. It does contain oxygen, but as you can see there, the oxygen is double bonded to the carbon and there's no hydrogen attached. So there isn't a hydrogen on that molecule that is having its electrons withdrawn from it. So propanone itself only has permanent dipoles. It has a very low boiling point, around about like 40 degrees or something. Don't quote me on that, but it's low. So I'm definitely not like water. However, propanone does dissolve in water. And the reason it does that is because it does still have a dipole and a lone pair on the oxygen, which means that although propanone can't hydrogen bond with itself, it can hydrogen bond with water. You don't need both molecules to have a hydrogen attached to oxygen, nitrogen or fluorine. You just need the other molecule to have a delta negative oxygen or nitrogen or something with a lone pair. So this explains also part of the reason why carbon dioxide is pretty water soluble. The other reason, by the way, is that it reacts with water, but on its own it is still quite a soluble gas. And it's for the same reason the C double bond O has a lone pair which can form a hydrogen bond with the hydrogen from the water. And in fact, so can the oxygen on the other side. So you can get hydrogen bonds between molecules where one of the molecules doesn't form. Last one we're going to look at then is our instantaneous dipole, induced dipole. You may call these London forces, you may call them van der Waals forces. My course actually calls them London forces, but I prefer to teach it as instantaneous dipole induced because it tells you what it does. So let's explain what's happening here. This is iodine. There is no difference in electronegativity, but electrons are moving randomly all the time between the two iodine atoms. So there is a cloud of electrons that's being shared across the whole molecule. Electrons move randomly and they move very fast. This means that if you were to take a little snapshot at any nanosecond in time, you would never have the same amount of electrons on both sides of the molecule. It's just not really likely because they're moving so fast and random. So you get what's called an instantaneous dipole. This moment where there just happened to be a little bit more electron density on one side of the molecule than there is on the other. Doesn't last very long, but it doesn't have to. So if it's then near another molecule, and this is important, so these are much stronger if the molecule is actually a liquid and the molecules are close together. Close together is quite important. Then that will induce a dipole in a neighbouring molecule. And obviously the dipole that it induces is because that negative charge gets near the iodine molecule on the right and will repel the electron cloud, and therefore the dipole that results, the induced dipole, will be an opposite charge where the delta plus is facing the delta minus and they will attract together. And that's how instantaneous dipole induced dipoles work. Everything has them, even single atoms like noble gases. And they can be quite significant depending on a couple of factors. So there are two main things which really influence the strength and the size of these attractions. One of them is more electrons. So at GCSE we're always talking about bigger molecules having stronger intermolecular forces. We learn about the halogens getting increasing boiling points as you go down the group, going from gas to liquid to solid. And this is because of not necessarily the size of the molecule, but simply that we have more electrons. So iodine has 53 electrons per atom, whereas chlorine only has 17. When you're comparing two molecules that have the same number of electrons, such as isomers, then instead you're looking at surface area. So if we were to consider three different isomers of pentane, you've got pentane, you've got methyl butane, and you've got dimethyl propane. It's easier to draw them as skeletal because then you could see that the longer and straighter the chain, the closer the two chains can get together, the stronger the forces between them. When you start putting branches in, it stops the two compounds being able to get as close, and they can't form as strong interactions, because remember, those dipoles need to be really close because they're very, very weak effect. We often think about surface area like things being scrunched up, like in biology. It's not like that in chemistry. So more branches means a lower surface area, because you're not making the molecule longer when you do that. We're considering isomers, so you're making it shorter and all kind of cannot pack together. Okay, so this is quite a complicated little flow chart, but it's not that complicated really. It's more just little rules to follow to try and answer an exam question about two compounds, say, that you're trying to compare. First thing, do they have the same strength of intermolecular force? Paul's accent's going a bit fast. So what we mean by that is compare them. Do they both have hydrogen bonding, or does one have hydrogen bonding and one not? If that's the case, it's really easy, because hydrogen bonding is stronger than permanent dipoles, and permanent dipoles are stronger than instantaneous-induced dipoles. And so stronger intermolecular forces just need more energy to overcome them, so you would have a higher boiling point. So something with hydrogen bonding would usually have a higher boiling point than something that only had instantaneous-induced dipoles. We do need to be careful with this, because, for example, in a polymer, like a really, really, really large molecule with a large number of electrons, the instantaneous dipole might be more significant. The other case that might happen is a molecule that contains, for example, a bromine atom, which is a large atom with a lot of electrons on it. Usually you would have a clue in a question like that, like you would know the two joining points, so you'd know one would be stronger than the other. Back at the start, what about if they have the same strongest intermolecular force? Well, if they both have permanent dipoles, maybe one of them has a stronger, more extreme dipole. That's quite rare. More common is that if they both have hydrogen bonds, that one of them has more hydrogen bonds than the other. For example, an alcohol with one OH group compared to an alcohol with two OH groups. Alternatively, water can form two lots of hydrogen bond per molecule because the oxygen has two lone pairs, whereas in ammonia there's only one lone pair. So there might be some opportunities for a molecule to make more hydrogen bonds than the other one. And then this is much more common, two molecules that both only have London forces or instantaneous dipoles. If one of them has more electrons, so is a bigger molecule, then we just go to the point that more electrons is stronger. Alternatively, if they're isomers, it must be that one has a greater surface area than the other. So we're going to now look at 4 examples. Let's see if we were to compare chlorine and bromine molecules and decide which one has the higher boiling point and why. You probably know the answer, but the explanation is what we're looking for. So, do they have the same type of intermolecular force? Yes, they do, because they're in the same group in the periodic table. They both only have ID. Does one have more electrons? Yes, they're not isomers. Bromine, therefore, is the one with the highest boiling point, and the reason for that is because it has more electrons. Let's stop saying it's because it's bigger or heavier, and therefore has a higher boiling point. Next pair of molecules that we're going to compare, often we have to compare organic molecules, and often we're only given structural formulae. So if I was given these 2 structural formulae, I need to be careful not to leap to conclusions. These are not both alcohols. So on the left we do have ethanol. I haven't drawn the whole molecule. On the right, that is ethanal, so it's an aldehyde. I know it must have a double bond O, because that's the only way that I could possibly have the right number of bonds at the end of that molecule. If that carbon only has 1 oxygen and 1 hydrogen attached, then they can't be attached to each other, otherwise we don't get 4 bonds around the carbon. So when you see HO, that's an aldehyde, not an alcohol. Okay, do they have the same type of intermolecular force? Well, no, they don't, because we have an O attached to an H here, and in the aldehyde the oxygen is not attached to the hydrogen. So between molecules of themselves, Ethanol would have hydrogen bonding, ethanal would not. So our explanation is that ethanol has hydrogen bonding. Hydrogen bonding is stronger than permanent dipole, and therefore ethanol has the higher boiling point because stronger intermolecular forces require more energy. Don't forget to link the strength of the intermolecular force with the energy, and this relates it to the boiling point. Third example that we're going to look at is going to be two different isomers. We brought this up earlier. So pentane and dimethylpropane. They both contain 5 carbons and 12 hydrogens. So pentane is unbranched, dimethylpropane is branched. Do they have the same strongest type of intermolecular force? Yes, they're isomers. They contain the same atoms. Does one have more electrons than the other? No, they're isomers. They are literally the same molecular formula. And so therefore we have to answer it in terms of surface area. So pentane is the unbranched version, so it has a greater surface area, it has more opportunities to create London forces, so it has stronger London forces or instantaneous dipole-induced dipole, and therefore higher boiling point. Last example we're going to look at, carbon dioxide versus sulfur dioxide. You need to be a little bit careful with these two, not just jump to conclusions and think that maybe they're both got dipoles and therefore we're just looking at electronegativity. It's more complicated than that. Carbon dioxide, carbon's in group 4, so when it forms 4 bonds, it has no lone pairs. But sulfur's in group 6, so when it forms 4 bonds, 2 with each of the oxygens, it has a lone pair. And we looked at this when we were drawing our covalent molecules in the other video. So because it has a lone pair, its shape is not linear, whereas carbon dioxide is a linear molecule. So sulfur dioxide does have an overall dipole moment. It has a positive end and a negative end. But in carbon dioxide, the oxygens are 180 degrees apart. So there's no dipole, even though the bonds are polar. So the CO bond is polar, but there's no dipole. So they don't have the same type of intermolecular force. Carbon dioxide only has instantaneous-induced dipoles, and sulfur dioxide has permanent dipoles. Permanent dipoles are stronger than instantaneous-induced dipoles, so that means they need more energy to overcome them, and therefore it's sulfur dioxide that has the higher boiling point. Hopefully that's been really, really helpful. It was a bit of a long video, but I think intermolecular forces is something that is new to A-level, and we often go through it quite quickly and can get a little bit left behind. The more that you practice and the more that you just follow that little example of going through the flowchart, then you'll find that actually there is a process and there's only so many different types of question they can ask you about that. So you know what's going to happen next. You're going to have to practice some questions on intermolecular forces and bonding.